Welcome back. One more problem. A student drops his graphing calculator from the top level of the parking garage, 64 feet high. All right, again, this is the equation for gravity. All right, and so that equation is going to be S of t equals negative 16t squared plus v naught t plus s naught. Right? The v naught, of course, is initial velocity. Right, so notice you do not see anything with feet per second. I'm going to assume the time is per second. Right, so t equals second. Right, because that's an expectation there. It would be per second. Right, so you notice you don't see anything with feet per second. Why not? He drops the graphing calculator. So if you're dropping something, you're just holding it in your hand. How fast is it moving if you're holding it in your hand? Right, so the initial velocity here, because it's dropped, is 0 feet per second. Right, you just dropped it. All right, so we want to find position, velocity, oh, sorry, and we forgot S naught. S naught is initial height. And that's going to be equal to, it's on top of the parking garage, so that's 64 feet high. All right, so let's find the position, velocity, and acceleration as functions of time. All right, so A, let's write our equation here. So S of t equals negative 16 t squared. All right, no point in putting 0 t, right? And then so that would be plus 64. And then, of course, v, our velocity equation, is just the derivative of position. All right, so that's going to be negative 32 t, and that's it, right? Because derivative of 64 would be 0. The acceleration is the second derivative of position. So a of t equals negative 32. All right, so we have written our three equations. All right, B, when does the calculator hit the ground? So we want to know when S of t equals 0. Nice, easy equation to solve here. All right, so 0 equals negative 16t squared plus 64. Let's factor out greatest common factor, which is a negative 16. So we have t squared minus 4. Well, that's an easy factor. So negative 16 times t minus 2, t plus 2. We can ignore this factor, right, the t plus 2, because t cannot be negative. That doesn't make any sense. So we have t minus 2 equals 0. T equals 2 seconds is when the calculator is going to hit the ground. So if you 64 feet up the ground and you just drop the calculator, 2 seconds, it is going to hit the ground. All right? We want to now know the velocity with which the calculator hits the ground. Right? In other words, we want to find v of 2. Right? Because that's how long it takes for the calculator to hit the ground. So we have v of 2 equals negative 32 times 2 excuse me, equals negative 62 feet per second. All right? And we're expecting the velocity to be negative, right, because we dropped it and it's hitting the ground. All right, so it's headed down, right? So we're expecting a negative velocity here. All right, D, what was the calculator's average velocity from the time it was dropped until the time it hit the ground? All right, so we're finding the slope of the secant line. All right, so what we're finding here is the average rate of change is going to be, so hit the ground in 2 seconds, right? So we're finding s of 2 minus s of 0 divided by the time, right? So so slope of the secant line is change in position over change in time, all right? Actually, let me just write that. If I move it over, I could. Whoops. Sorry about that. Oh, now I got to make everything fit the way it was. There we go. Right, so change in position over change in time. Right, so d, our average velocity, the average rate of change, is going to be, so s of 2 be, let's plug that, we have s of 2. All right, s of 2 is 0, right, because the position, right, was, oh, I'm sorry. Sorry, I was calculating out average change in position. I'm sorry, I misread the question. Ignore that part. Let's just read the question very carefully. Average velocity. All right, so just to redo that. So what we're actually finding is our average rate of, let's just put average rate of velocity because that's the change we're looking at, is going to be, for the so the time it was dropped to the time it hit the ground in 2 seconds. So v of 2 minus v of 0, right? This was, hits the ground. And this was dropped. Divided by the change in time. So 2 minus 0. Sorry. It's a good thing I looked at that. All of a sudden I looked up and I'm like, oh, no, change in velocity. So we'll just call it, we'll make up our own letters here. Average rate of velocity here. All right, so v of 2, we have negative 62 feet per second. V of 0, we also have 0 feet per second. All right, so that's going to be negative 60, got a funky 6 there. Negative 62 minus 0 divided by 2 minus 0 is negative 32 feet per second is the slope of the secant line. The slope of the line that would be connecting our initial velocity and the velocity when it hits the ground, right? Because then that's it. It's not moving anymore. All right, so was this smart to drop such an expensive calculator from so high up? Well, I guess that's, this one here is an opinion question. But I would say no. That calculator is probably not working anymore. And now you got to buy a new calculator. Right? So, and you need a calculator on the AP test, you need a calculator in the class. So, no, it was probably not such a good idea to drop your calculator. If you feel you need to drop something, well, drop something, it doesn't matter, right? Definitely not the calculator. And that's the end of this question. So, thanks for watching, and bye for now.